Hi guys, this is AP Chem, Chapter 17, Section 2 on buffers. We are going to look at the textbook and take down some notes about buffers. So there are two possible options to have a buffer system. The first one is a weak acid and its conjugate base. So a very common example would be acetic acid, that's vinegar. Okay, and its conjugate base would be the anion of this. So it's going to be in equilibrium with CH3, COO minus. And usually the way that we get this second one is by adding the salt of that ion. So we could add sodium acetate, for example. A base, a weak base, like NH3, and its conjugate acid, so that would be in equilibrium with NH4 plus. And so again, we could have ammonium chloride as the salt that we could add. But there's another way that we can get that as well. So basically it's this little partnership. We call them conjugate acids and bases. And the only difference between the left and the right of both of these, even though we're talking about an acid and a base, the difference is an H plus. Okay. So H plus being added to the right side would shift it to the left, or being added to the left would shift to the right. So it's an equilibrium system where the hydrogen can be either removed or added, and the system will adjust. That's Le Chatelier's principle. It's going to adjust to reestablish that equilibrium. Okay, so let's write down a few things in our Jamboard. So this is going to be chapter 17.2, a buffer. The very broad definition of a buffer is, let's see what your book says. It resists pH change by neutralizing added acid or added base. It is, I'm going to call it an equilibrium system that resists change in pH. Okay, so if you add an acid, it's going to try to neutralize that acid in a way that the pH doesn't go up or down too quickly. And if you add a base, it's going to try to alleviate that change as well. Okay, so it resists change to pH. We can have buffers of all kinds of different pHs. For example, in our stomach, we could have an equilibrium system going on where we want the pH of our stomach to remain very low. We want it to be acidic. There's hydrochloric acid in there. So you can have a buffer with a pH of 2, for example. Or we might want a system where the pH is stable, but it's a base. So it could be something like a pH of 11. So it doesn't matter. It doesn't have to always be a neutral buffer, like a pH of 7, and it doesn't change. A good example of that would be our blood. We do want the pH of our blood to remain very close to neutral, about 7. It's not exactly 7. I believe it's a little bit above. But we want it to remain constant, and we want it to be about neutral. So that is a buffered system with a pH of 7. But it could be anywhere from 1 to 14, and it's just going to resist changing of that pH, that set pH. Okay, so how do we get a buffer? There are two ways to get a buffer. This picture is showing us one way, and that's what I mentioned earlier. We are adding our weak acid, and look at that, acetic acid. I told you it's very common. And then they're adding sodium acetate. Why are they adding sodium acetate? Because that will ionize Na+, and the acetate, CH3COO minus, and we will have a mixture. So if you can, let's zoom in, if we can see this diagram right here, we will have the H pluses floating around. Actually, this is Na. Okay, so we have sodiums floating around. Those are spectator ions. They're not going to do anything, but observe any kind of reaction going on. But I have this negative right here where there are 2 oxygens on the carbon and no hydrogens versus this one on the left that is going to have a little hydrogen attached to it. So like this is my acid right here. This one is going to be the acetate. Okay, so let's label them. This one's going to be negative. This one is neutral. It's the acid. This one is negative. All the ones that are missing that hydrogen on there are going to be negative. So we're looking at the oxygen. See there, right there is a little hydrogen. So that is my acid. And then this one is missing the hydrogen attached to the little red oxygen. So that is my negative acetate ion. So what do I have going on? I have HC2H3O2 in equilibrium with, I have that Na plus in there, but since it's a spectator, I'm going to leave it out. It's in equilibrium with C2H3O2. Okay, plus we have to add, wait to confuse you guys, this is a negative ion, plus the other thing that it's going to be added is the H plus. Okay, so in this equilibrium, it has reached a balance point, okay, where the 2 remain constant. So as one reacts, the other one is going to unreact, and they're happening at equal rates. Now, if I do something to disturb the system, like let's say I add a few drops of HCl, okay, how does this buffered system resist a change in pH? This H plus is going to completely ionize from the HCl, and I'm adding to the right side of my buffer here, I'm adding H plus. To get rid of the H plus that I just added, some of that H plus is going to attach to the acetate that's floating around and turn back. It's going to shift towards this reactant. It's going to shift to the left, and it therefore then removes the added H plus that I just put in there. Okay, there is going to be a little bit more than there was before, but it's going to shift in a way to reduce that amount and increase the other side until I reach an equilibrium again. Okay, so that is my buffered system. Okay, and it's just one example. I said there are 2 ways to make a buffer. Let's write down the first way. 2 ways to make a buffer. Number 1 is to add weak acid plus its conjugate base, and in parentheses, that conjugate base is the salt. Okay, it's the anion of that. So in my example, I had CH3COOH, that was my weak acid, acetic acid, plus the conjugate base of that was sodium acetate, CH3COO. Okay, so I have the conjugate base of acetate and then my weak acid, or I could add a weak base plus its conjugate acid, okay, and allow them to come to equilibrium, and then we're going to have a buffer. The other way is a little more complicated, and that is to start with a weak acid and add half the amount of a strong base. Okay, let me go over what in the world that means. Okay, so buffer type 2, how do I do that? So if I had CH3COOH, okay, in solution, and let's say I have 0.2 molar of this guy, okay, I want it to get to an equilibrium point with my acetate, my CH3COO minus, if I react this with NaOH, it's going to be a reaction that the Na, spectator ion, it's just going to be floating around, the OH, which is negatively charged, is going to basically, it's all of the OHs in this strong base is going to neutralize. It's going to rip off the hydrogens from my acetic acid. So two things, I would have to have 0.2 molar of this. Let's say I have 100 milliliters. I want to get a buffer. I want them about 50-50. We'll talk about that later in the amount of my product and my reactant. So if I have 100 milliliters of 0.2, if I react that with 50 milliliters of 0.2, this is a 1-to-1 ratio. So I'm getting rid of half of it. So that half is going to take away the OH, and I will end up with a certain amount of CH3, COO minus, okay? And then water, because of the H plus and the OH minus that's going to form, and the Na plus that's floating around, Na plus H2O. Okay, so basically, if you start with a weak acid and you add half of the amount of a strong base, you're like setting up this kind of system where you have the weak acid and its conjugate base. It's just another way to get there. Okay, and we will be doing a lab, hopefully, that uses this second method. So I think it'll make a little more sense when we get there. All you need to take away from this first part is that a buffer resists change in pH because of that equilibrium system. Okay. All right. So that is what a buffer is. And this is a very important fact right here. It's italicized. A buffer must contain significant amounts of both a weak acid and its conjugate base, or vice versa, meaning a weak base and its conjugate acid. Usually it's the acid, so that's why we keep using that example. Okay, but it can be a base with its weak acid. A weak base and its conjugate acid. Okay, and oh, look at that. They also give the exact same example that I just told you guys. If you mix NaOH with acetic acid, the OH is going to still the hydrogen. So these two little parts will come together to neutralize and make water. And then I drew them separately as Na plus and C2H3O2 minus, but they drew it as the molecule, sodium acetate aqueous. Okay, and over here, see that acetate is the conjugate. Let me get rid of my little picture. Conjugate base of my acetic acid. So this is acetate is in equilibrium with acetic acid. Okay, they're a partnership, and the only difference between the two is that H plus. So you can use H plus to shift left and right to resist the change in pH. Okay, so a summary, they resist change in pH for the 100th time. A buffer contains a significant amount of weak acid and its conjugate base, or weak base and its conjugate acid. The acid neutralizes any base that's added, and the base would neutralize any acid. So this is the Y. Okay, when you add to one side, it shifts the other way to help neutralize and resist a change in pH. Let's look at this conceptual connection. What is the buffer? So we have weak acid, strong acid, weak, weak. It's not a strong acid, so I know it's not B. And which one of these would have the conjugate base of HNO2? The conjugate base of that would be NO2 minus. So which one of these has NO2 minus? HCl, no, that's a strong acid, so no. Is it NaCl? No, it is not. So the answer is D. You see this NO2? It's with sodium. The sodium will ionize. You get Na plus, NO2 minus, so the answer is D. Okay. And calculating the pH, we are going to just very briefly talk about this. We're going to calculate these in class tomorrow. So a common ion effect is exactly what it sounds like. The common ion is something that both the reactant and the product has in common. Okay, and it's an ion, so it has a charge. And the effect is like what's going to happen. So the common ion for these guys, moving down here to our example, the common ion is that the acid right here, acetic acid, is going to release some of that. It's a weak acid, so only a few, but it's going to release some of the H plus, and it's going to make an acetate ion over here. And then the Na, C2H3O2, is also going to release that CH3COO minus, that acetate. So what do they have in common? They have this guy in common. Okay, the acetate is in common. So for this example, calculate the pH of a buffer solution. It has 0.1 molar acid and 0.1 molar salt. We're going to do an ice chart just like we've been doing. The initial concentration of my acid is 0.1. That's given in the question. The initial concentration of my H3O plus is approximately 0. Remember, it's actually 1 times 10 to the negative 7, but that's a tiny amount, so we could say it's basically 0. So we're going to ignore this. The amount of my product now in this case, because it has reached equilibrium and this is a buffer, I actually start with this amount of my acetate ion. So I start with 0.1 on both sides. Okay, this is going to be a good buffer because they're present in equal amounts. And what's going to happen? The acid is going to go down by a certain amount, and the acetate over here is going to go up by a certain amount. And the H3O plus also goes up since it's a product. So I will get 0.1 minus x, and then look at this one is 0.1 plus x over here. Okay, so this is our equilibrium concentrations that we just figured out. Plug those in to the Ka expression. Okay, and look at x is small. How do I know that? I know because of the Ka. It says use the table to find Ka, table 16.5. Ka for acetic acid is 1.8 times 10 to the negative fifth. Anything that's about times 10 to the negative fifth or sixth is pretty certain that you can use x is small. And on the AP test, they only use x is small. So 0.1 minus x just becomes 0.1 right here. And 0.1 plus x just becomes 0.1 up here. And so they use that to solve for x. And since you have 0.1 over 0.1, they cancel. So x is this value. And then it said find the pH. Well, that equals H3O plus. Always label this, please. So the pH is just the negative log of that. Negative log of 1.8. 1.8 times 10 to the negative fifth. It's going to be something close to 5 because it's the exponent of 10. 4.74 is my pH. Okay, so the only difference is we're doing an ice chart just like any other equilibrium, but these equilibriums are special in that we have our acid on the left, and we are starting with a certain amount of the conjugate base on the right. Okay, I would like you guys to try these 4 practice problems and just see if you can do them, and we will come back and go over this tomorrow. Okay, I hope you guys have a great day. See ya.